focusing on a key aspect of functional programming, something we'll use extensively in our Haskell coding: higher order functions. So what are higher order functions? The idea of a higher order function is to treat functions as first-class data. In functional programming, functions are first-class data, meaning that they can be passed as arguments to other functions or even returned as results. You can build new functions as the result of other functions, and this is one reason why Haskell and languages like Haskell are so effective. They provide many ways to build functions by combining other functions. Some simple examples that I briefly covered in the last lecture are functions like map, which encapsulates the pattern of applying a function to every element in a list. So if we have a list, we can map a function over that list, meaning we produce a new list by applying the given function to each element in the original list. The size of the result list will be the same as the size of the input list, but each element may be transformed by the function. The exact transformation depends on the function's behavior and, of course, its type. For example, we might use a function from int to bool to determine whether numbers are even or odd, resulting in a corresponding list of Boolean values. A similar function is filter. Here the function keeps elements from the list based on a condition, or you could think of it as filtering out elements that don't satisfy a given predicate, which is provided as an argument. Okay, so let's try out these functions in the terminal to understand them and their types. Conceptually, they're quite simple, so this should be straightforward. So, what's the type of map? The first argument to map is, of course, a function, which is what makes map a higher order function. It takes a function as its argument. Map is very polymorphic or generic. It uses a provided function to transform a list of elements of type A into a list of elements of type B. And here, A and B can be any types, but the function must map the types of the arguments and the result that you want. So for example, if we have a function that takes an int and returns a bool, then we would pass it a list of ints, and map would return a list of bools as a result. There are no other type constraints, so it's quite flexible. Any questions so far? Now let's look at filter. Its type and structure looks similar to map, but the function provided to filter must be a predicate. It must return a Boolean value. This tells us which elements from the list to keep, so the result will be a subset of the original list. Hopefully at this point you will be comfortable with the concepts of filtering and map. Now, how are these functions actually defined? They can be defined in several ways, such as through recursion, and you'll see examples on the slides. Another way to define them is using list comprehensions, which gives a very concise syntax. I'll rename the example function map_prime to avoid conflicts with the original map. Using a list comprehension, we can define map as follows. This definition states that we apply f to each x taken from the list x's. This is a very simple way to define map and shows that in many cases you could choose to use a list comprehension instead. Filter can be defined in a similar way. It's the list of all elements x from x's, the list x's, such that the property that f of x is true. Actually, following standard naming conventions, we usually use p for a predicate rather than f for a generic function. As you can see, map and filter are closely related to the power of list comprehensions. List comprehensions thus are like combinations of maps and filters, and even more general, so you can have multiple generators in a list comprehension. But map and filter are the simplest examples of higher order functions that you'll encounter often in code and will likely use frequently in your own projects.